So last time we talked about exponentially weighted moving averages, but we didn't mention anything about momentum. Now I'm here to sort of do that. Over here, we had talked about how we can visualize gradient descent as a ball going down. And so what happens is that the parameter updates for gradient descent might be very, very noisy, essentially. You might at one time tell, so if this is W, right? If you're at this value of W, you might be told to go this way and then 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 go this way, right? So it might be very noisy and how much you move and whatever. Maybe you want to smoothen that out, right? So for a particular value of W, let's say we plot W on the x-axis and actually not W, but actually time. Not W, but time. Or like iteration number, right? And this is our iteration, the number of steps of gradient descent. So iteration number for gradient descent. And on the y-axis, we put dj dw, right? And assuming that w is a scalar, dj dw is a scalar, or a scalar meaning just a number, right? It's not like a vector or like a matrix or something like that. So let's say that this would be zero, right? This is the zero axis, right? And sometimes it's up here on time step one, and then it goes down here, up here, and then down here, and then eventually it's like this, and then slowly as we complete training, the DJDW settles around zero because there's not much to learn anymore, right? And that corresponds to the ball being at the center of the half pipe that we talked about before. And as you can see, this kind of could look really noisy if you do this in a real practical setting. So instead of following this trajectory, right? Instead of following that trajectory, if you applied an exponentially weighted moving average to this, what you could do is you could transform this into something that looks more like this, right? And so it looks much smoother, right? And so these arrows would essentially like be instead of like this, it would be more like from here, it would be like, move a little bit here and then move a little bit here. And it would basically be less noisy than than the original thing, right? So assuming this is noisy, this would be less noisy, right? Um, there's another visualization which is over here, like gradient descent would tell you to go right and then left and then right and then left, right? So, but now that you're already going right, it would basically, the exponentially weighted moving average would have you continue moving right and very slowly turn left. And essentially, you would settle much quicker, I guess. Instead of going right and then left and then right and then left, you would sort of, now that you're already moving right, it would kind of have you keep going that direction. And once it turns left, the original gradient descent turns left, you would not turn left as quickly. You would kind of just go to the left a little bit, and then you would be guided to the right again. And so it would give you a more direct path to the minimum than just using normal gradient descent. So what I'm saying is that you keep on, so you have this value of, let me switch back to black. You have this value of W0, right, which is your initial guess, then W1 and W2 and so on and so forth. And what you want to do is you want to create a new value of W's, let's say, which is like W prime 0, W prime 1, W prime 2, and so on and so forth. And so what you could do is define wi prime, right? So this is for the new series. For the new series, any given term at a time step I is equal to, let's say, 0.9 times W0 plus, not W0, Wi plus 0.1 times W I minus 1 prime, right? So this is the previous value in this sequence, and then this is the new value coming from this sequence. So you still perform the same gradient descent, and you're getting the parameter updates the same exact way. And sorry, I didn't mean to do W over here. I meant to do DJ DW0. Sorry, DJ DW0. It's the same idea, but you're not taking an exponentially weighted moving average of the W's themselves. You're taking an exponentially weighted moving average of the derivatives. So this is, so remember, we have W is equal to W minus alpha times DJ dW, right? So we're taking an exponentially weighted moving average of this, which corresponds to the update. And so the idea is that if instead of using DJ dW over here, we're using a smoothened version. Let's say we actually call this not derivatives, we call this V, V0, V1, V2, and so on and so forth, right? So this is W equals W minus alpha times V whatever, right? V at this particular time step, right? And so what this would correspond to, the hope is that this would be smooth updates. So this is the update. And so the hope is that by having VI be an exponentially weighted moving average of the derivatives, right? So instead of having exactly this, you have an exponentially weighted moving average of all of the previous derivatives. This would correspond to a very smooth update where your updates are kind of like all in the same direction rather than, sometimes you're turning left, sometimes you're turning right, like I showed you before. And so, sorry, I just want to fix this equation right here. This is not the W's themselves. It's the update for the W's. So V at any particular time would just be equal to whatever the new value, let's say 0.9 times whatever the new value for the derivative was, plus 0.1, let's say, times V I minus 1. So this is the previous time step, right? And so this smoothing would allow you to have smooth updates, right? And yeah, I guess that's all I wanted to tell you about.